Hello everyone, welcome to NPTEL online certification course on fundamentals of food process engineering. In the last class we were discussing about the different types of evaporators. So, today we will continue the discussion on evaporation and concentration. So, we have discussed in the last class about the multiple effect evaporators. Multiple effect evaporator is one way by that we can improve the efficiency of an evaporation system. And if we talk about improving the efficiency, so generally efficiency we define by the output effect that we are getting divided by the input energy that we are giving to the system. So, using multiple effect evaporator, we can increase the vapor that is being evaporated from the system, whereas we can utilize the same amount of steam that we can use in a single effect evaporator. So, that is one way to increase the steam economy, that is steam needed to evaporate the amount of vapor from the liquid that we are concentrating using the evaporation. So, today we will discuss the same thing, that is the multiple effect evaporator and other mechanisms by which we can increase the efficiency. So, in the multiple effect evaporator, if we just recapitulate that. Okay. So, in multiple effect evaporator what we did is, suppose this is the first effect, okay, and in series there is other two effects, that is the second one and this is the third one, right. So, steam enters into the first effect, let us say Ts temperature, and this steam is utilizing here to evaporate the liquid from the feed, okay, feed F that is entering at Tf, and the temperature here in the first effect is T1, in the second effect it is T2 and third effect is T3, and the corresponding pressure prevailing in all these chambers are P1, P2 and P3. Now, the vapor produced from the first effect is going to enter into the second one, okay, and similarly the vapor produced from the second effect is going to introduce in the third one. So, this vapor will be condensed here in the second effect and give the latent heat of condensation that is being utilized by the feed that we use here, which is the concentrated feed that is coming out from the first effect, and then similarly from the second effect the concentrate which will come will be utilized as the feed in the third effect, right. And finally, the vapor which is coming out from the third effect at the temperature of T3 will be going to the condenser, right. So, what will happen that if our first effect operates at atmospheric pressure, so this vapor that is coming out at that atmospheric pressure and temperature will be again condensing here in the second effect. So, temperature T1 must be greater than T2, right, or pressure P1 must be greater than the pressure P2 in the second effect. Similarly, the vapor which is coming out from the second effect will going to condense in the third one. So, T2 will be greater than T3 and the pressure P2 will be greater than P3. So, definitely the vapor that is coming out from the last effect will be this is coming at a vacuum, because P1 which was our atmospheric pressure is higher than P2, P3. So, except the first one, the other two effect must be operate under vacuum. Therefore, we can say that the vapor from the last effect are usually living under vacuum, and these vapors must be condensed and discharged as a liquid at the atmospheric pressure, right. This condensation can be done by using the cooling water. Now, the type of condenser, if we look into, there is one surface condenser. That means, there is a heat exchange surface is provided, okay, one side of which there is a steam and the other side there is a liquid. So, the vapor to be condensed and the cooling liquid are separated by a metal wall. The other method is direct contact condenser, that is where the vapor and the cooling liquid are mixed directly. So, coming to first the surface condensers, here no mixing of the condensate with condenser cooling water is done, because there is a heat exchange surface. So, across which the heat is being transferred. So, no mixing of the condensate with the condenser cooling water is done here. Shell and tube condensers with the vapor on the shell side and the cooling water in multi-pass flow on the tube side. Okay. So, that is one case. We will discuss in detail the heat exchangers in the other chapters. So, also with the vapor there are some non-condensable gases usually present. Okay. So, this can be air or carbon dioxide, nitrogen or another gas which may have entered as dissolved gases in the liquid feed or occur because of the decomposition in the solution. So, these has to be removed from that vapor. So, these non-condensable gases may be vented from any well cooled point in the condenser, and if the vapor being condensed is below atmospheric pressure, as the case may be when the last effect is operated under vacuum, the condensed liquid leaving the surface condenser can be removed by pumping and the non-condensable gases by a vacuum pump, right. So, because from the low pressure to the high pressure we need to take them out, the condensed liquid, that is why we need to pump them. Okay. Then surface condensers are much more expensive and use more cooling water. So, they are usually not used in cases where a direct contact condenser is suitable. That means, since we are using a proper defined geometry, that is the tubes inside the shells where the steam is in, and we need to define all those geometry, length of tube, the thickness, okay, everything, and designing of this and fabrication is a cost involving affair. So, where the direct contact condensers can be used, there we avoid any kind of surface condensers. So, direct contact condensers. Now, we will look into direct contact condenser. One example is counter current barometric condenser, right. So, what happened here, the vapors which is coming from the evaporator effect, that is first coming into the condenser, the barometric condenser, okay, and then that is being cooled by, condensed by the water which is falling on or getting directly mixed with the vapor. So, this kind of condenser generally the condenser is kept over a long distance from the discharge end, because to accommodate the water column that is established in the pipe for differences in pressure between the low absolute pressure in the condenser and the atmosphere, right. So, because of atmospheric pressure, it try to maintain a liquid column inside the the direct barometric condenser. So, that is why we need to keep the condenser at a specific height above the discharge level, and these are very inexpensive and economical in terms of water consumption. So, here maintain a high vacuum corresponding to a saturated vapor temperature within about 2.8 Kelvin of water temperature leaving the condenser. Okay. So, now, water consumption in the direct contact condensers. So, how we can calculate the total water consumption in case of a direct barometric condenser. So, the vapor flow to the condenser, if we assume that is V kg per hour, okay, V kg per hour, in this rate the vapor flow is coming to the condenser at a temperature of T s, and the water flow is W kg per hour at an entering temperature of T 1, and this water leaves at a temperature of T 2. Okay. So, then what will happen, that the heat which will be given by the V kg per hour vapor will be taken by W kg per hour water, and the temperature of this will increase from T 1 to T 2. So, making a heat balance, we can write V into capital H s, which is the enthalpy from the steam table of the vapor at T s Kelvin. So, V into capital H s plus W, that is the mass flow rate of liquid water, into Cp, specific heat, into T 1 minus 273.2, that is equal to V plus W into Cp T 2 minus 273.2. Okay. So, W by V, that is kg of water divided by kg of vapor, is coming as capital H suffix s minus Cp T 2 minus 273.2 divided by Cp into T 2 minus T 1. Okay. So, from this we can calculate the water consumption per kg of vapor needed in the direct barometric condenser. Okay. Now, the vacuum pump that is used can be mechanical pump or steam jet ejector. In the ejector, high pressure steam enters a nozzle at high speed and entrains the non condensable gases from the space under vacuum. Jet barometric condenser, that is another type of condenser that is being used, where high velocity jets of water act both as vapor condenser and as an entrainer of the non condensable gases out of the tailpipe. So, jet condensers usually require more water than more common barometric condensers and are more difficult to throttle at low vapor rates. So, another way of improving the evaporator efficiency is the vapor recompression. So, that means we are somehow increasing the pressure of the vapor that is coming out of the effects of the evaporator. Okay. So, compression. So, compression of the vapor generated by evaporation increases its saturation temperature. So, the vapor that is if we want to draw this. So, if we take a single effect evaporator as well, this is steam entering at Ts temperature and this is feed at Tf, and here it is T1 temperature, P1 pressure and the vapor V which is coming out at T1. Now, if the vapor is being compressed, that means we are increasing the pressure from P1 to P2. So, this is kind of a reversible adiabatic compression. Okay. So, reversible. So, there is no change in the entropy and again adiabatic. So, entropy is constant in this case. So, isentropic compression is assumed and the compressed vapor is introduced to the steam side of the same evaporator. So, here we are not going to increase the different effect, but within a same effect we just recompress the vapor that is coming out of the effect and then we are reusing it in the steam side section of the evaporator. So, the vapor recompression can be of two types. One is the mechanical vapor recompression, another is the thermal vapor recompression. So, mechanical vapor recompression. So, if we look into this diagram, so this is a single effect evaporator, okay, where steam is entering from steam is entering from this section, okay, and that is condensing, condensed liquid is coming out from this side. The feed which is sending to the entering to the evaporator from this bottom and then it is evaporated in here, okay, and all the vapor that is being separated is going to this mechanical vapor recompression device and then it is compressing the steam, increasing its pressure and then adding some makeup steam to it, and that steam is again utilizing that is being again utilized for the evaporation process. So, here we are getting a higher efficiency with single effect only, but by the application of vapor recompression. So, the enthalpy of the vapor is increased to that of the original steam. Okay, so, in this process the steam economy is increased, that means using 1 kg of steam we can increase higher amount of water evaporation that we can get. So, that is how steam economy is increased. Makeup steam will be required, okay, and this requires a large compressor. Generally positive displacement compressors are used. So, another method is the thermal recompression. Here by injecting high pressure steam via a nozzle or steam jet ejector, we increase the pressure of it. It has the ability to handle very large volume of vapor and can operate at lower pressure. So, there are no moving part as it needed for mechanical vapor recompression. So, no power requirement is needed. The major disadvantage is that optimum operation of this device occurs at a specific pressure and temperature. That means, if there is any kind of variation in the condition, that is the steam, the amount of steam that is being generated, or any variation in the pressure and temperature of that if happens, then it cannot perform. Okay. So, variation of condition in the evaporator may well lead to reduction in the economy. So, that is about the thermo recompression. Now, next we will see the effects of processing variables on evaporator operation. First is the effect of feed temperature. Now, how the feed temperature is going to affect, because we generally try to increase the efficiency of an evaporator. So, feed temperature if well below the operating temperature of the evaporator, then what happen, we need to heat the feed to the boiling temperature. So, we need more heat and more heat transfer area is required. So, to minimize the extra heat needed to increase the sensible temperature, sensible heat of the feed, we can preheat the feed and then we try to enter it near the temperature that is prevailing inside the effect of the evaporator. So, that can be done. So, one point is preheating the feed, that can reduce the heat transfer area and size of the evaporator. Next is effect of pressure. So, this is also very clear by now that corresponding to the pressure, the saturation temperature we can see from the steam table, and that is the temperature that is being present, or that is the boiling temperature of the liquid in the evaporator. Now, by any means if the pressure is changed, so the saturation temperature or boiling temperature will also change. So, reducing the operating pressure increases the delta T. That means, if the pressure is reduced or the vacuum is being generated inside, so delta T will increase and results in decrease in area, because the overall heat transfer Q, that is equal to overall heat transfer coefficient into area into temperature difference, right. Q, that is equal to U A delta T. So, if somehow this delta T is increasing, that means A will decrease to get the same heat transfer effect, right. So, therefore, reducing the operating pressure increases the delta T and results in decrease of the heat transfer area. Then Effect of steam pressure. So, using higher pressure saturated steam increases the delta T, right, which decreases the size and cost of the evaporator. Definitely, because if delta T increases again by increasing the pressure of the saturated steam, then we are getting a higher heat transfer by having a lower surface area. So, that thereby we can design smaller evaporator, smaller size of evaporator for the same heat transfer rate, and the cost will be reduced. The next thing we will going to cover is boiling point elevation. So, this is an important phenomena because there are a difference in the boiling point of a solution corresponding to the pure water. The difference between the temperature of boiling solution and the temperature of pure water, boiling of the pure water at the same pressure is known as the boiling point rise or sometime boiling point elevation. So, as evaporation proceeds, what happened that the liquid that we have taken for evaporation becoming concentrated more and more, okay, and this will cause rise in the boiling point in the evaporator. So, in multiple effect evaporator where the effects are fed in series, so the boiling point will rise from one effect to the next as the concentration rises. So, based on the concentration the boiling point elevation happens. So, as the concentration increases, boiling point elevation will also increase. Now, there is a chart which is called During's plot, which can give us an idea that how the pure water boiling point and the solution boiling point varies, and we have seen that they have a linear relation. Okay. So, if we see the During plot, it looks like the boiling point of water, okay, either in degree Fahrenheit or boiling point of water in degree Celsius, and also with that we have the boiling point of sodium hydroxide solution, okay, both in degree Celsius and degree Fahrenheit. So, we have pure water, the bottom curve, and then 10% NaOH, 20%, 30%, then 40, 50 up to 60%. Okay. So, from this we can get an idea that the boiling point elevation because of the dissolved NaOH into the liquid water varies from the boiling point of pure water linearly, and we can calculate them from this chart. For example, let us say the boiling point of pure water is boiling point of pure water at certain condition is 75 degree Celsius. Now, if we want to calculate the boiling point of 40 weight percent NaOH in the similar condition, so this curve which is corresponding the 40 weight percent NaOH and the boiling point of water which is showing 75 degree Celsius. So, we will look for the intersection of that, and then we will find the point which is the boiling point of the 40 weight percent NaOH solution, and the difference between these point and these point, okay, this is 1.1 and 0.2. So, boiling point between these two will give us the boiling point rise or boiling point elevation. Okay. So, at a particular temperature, at a particular pressure, the relationship between the pure water and dissolved material in that will generally follow the linear relation. Okay. So, during line is for NaOH solution, and for other we can also calculate it. So, here we will solve one example that the pressure in an evaporator is given as 25.6 kilopascal or 3.72 Cia, and a solution of 30% NaOH is being boiled. Determine the boiling temperature of the NaOH solution and the boiling point rise of the solution over that of water at the same temperature. Okay. So, what is given here? The pressure in the evaporator, that is given, okay, and solution of 30% NaOH is given. So, what we can do is, first corresponding to 25.6 kilopascal, what will be the saturation pressure of pure water, saturation temperature of pure water, that we can find, and later on we can read from the during plot that for 30% NaOH and the boiling point of pure water corresponding to this much pressure, what is the boiling point of the solution. Okay. So, we have seen that from the steam table 65.6 degree Celsius, that is the saturation temperature or boiling point of pure water at this pressure. From the during chart 65.6 degree Celsius and 30% NaOH, boiling point of the NaOH solution is coming around 79.5. Okay. Now, those who are not familiar with steam table, I think I have here one to show you. So, this is the properties of saturated steam and water, that is called steam table. This is in SI unit, you can get in other units as well. So, this is available in most of the unit operation or food engineering book index appendix section. So, here we need to find the vapor pressure that has been given something between these two, 25.03, and I think the next one is so here 25.6 kilopascal, okay, 25.6 kilopascal. So, 25.03, the temperature is 65, okay, 25.03, the boiling point will be 65 and 31.19. So, boiling point in 70. So, in between these two we need to interpolate for 25.6 kilopascal, and that is coming around the temperature that we have measured. Okay. So, that is 65.6, and from the during chart we have read 79.5 for the solution of 30% NaOH. So, 79.5 minus 65.6, that will be the boiling point elevation. Okay. So, we will stop here and we will continue in the next class. Thank you.